Hey everyone and welcome. Today we're going to do something a little different. We're going to follow a single, tiny ray of light on its incredible journey. And by the end of it, you'll have a whole new way of understanding, well, pretty much everything you see. So yeah, let's dive right in.
Think about it for a second. How is it that we can use light to see across the entire universe and at the same time peer inside a single tiny cell? It sounds impossible, right? But the secret is that light, for all its complexity, acts as our messenger. And the key to decoding its messages is something called ray optics, which boils everything down to just a couple of simple, fundamental rules.
So let's meet the hero of our story, the ray of light. Now you might be thinking, isn't light a wave? Well, yes, it is, but for almost everything we're going to talk about today, we can think of it as just a straight line, a path. That's it. This one simple idea, that light travels in a straight line, is the bedrock for understanding everything from your bathroom mirror to camera lenses to how your own eyes work.
All right, so our light ray is zipping along in a straight line. But what happens when it runs into something? Well, it really only has two options. It can bounce off or it can bend as it goes through. That's pretty much it. So let's start with the first one, bouncing. And this brings us to reflection. You already know this one, even if you don't think you do. It's what's happening every time you look in a mirror. A light ray hits a surface and it bounces. But here's the cool part. It's not random. It follows a really simple rule. The angle it comes in at is the exact same as the angle it goes out at. Think of it like a pool ball hitting the side of the table. Simple, clean, and totally predictable. It's why your reflection is always, well, your reflection.
Okay, but flat mirrors are one thing. Things get really interesting when we start curving them. And believe it or not, we have a formula that can predict exactly what a curved mirror will do. It looks a little intimidating, but it's not, I promise. It just connects three pieces of the puzzle. There's U, which is just how far away the object is. There's V, which is how far away the image appears, and F, the focal length, which is just a fancy way of saying how curvy the mirror is. With these three little variables, we can calculate everything.
All right, so that was bouncing. What about bending? Well, physicists have a name for that too, refraction. And you've seen this a million times. Ever put a straw in a glass of water and it looks like it's broken right at the surface? That's refraction. It happens because light actually changes speed when it goes from one thing to another, like from air into water. And that change in speed forces it to take a little turn, to change its direction.
And just like reflection, this bending is not random at all. It follows a precise mathematical rule called Snell's law. Again, don't let the formula spook you. All it's doing is telling us exactly how much that light ray is going to bend. It just looks at the angles and this one special number for each material, n, which is called the refractive index. You can just think of n as a light slowing score. Air has a low score, water has a higher one, and diamond has a really high one. The bigger the difference in the score, the more the light bends. So check this out. This is a perfect example of refraction playing a trick on our eyes. When you're looking at, say, a fish in the water, the light from the fish travels up and bends as it leaves the water to hit your eye. But here's the thing. Your brain doesn't know about refraction. It just assumes that light always travels in a straight line. So it traces those bent rays backwards to a point where it thinks the fish is, which is always shallower than where the fish actually is. It creates a little illusion, a virtual image. And that right there is why the deep end of the pool never looks quite as deep as it really is.
Okay, so we've got our two basic rules down. Bouncing and bending. Reflection and refraction. But this is where things get really cool. Because when you start pushing these simple rules to their absolute limits, you get some truly mind-bending results. This is where light starts to show off.
So let me ask you a question. We know that when light goes from water into air, it bends away from the normal, right? But what if you keep changing the angle? What if you shine the light from a really low angle from inside the water? Is there a point where it bends so much that it can't even get out?
Well, the answer is a big yes, and it leads to this incredible phenomenon called total internal reflection, or TIR for short. It's like a secret escape hatch that doesn't open. But for it to work, you need two things. First, the light has to be going from a slower material to a faster one, like from glass to air. Second, you have to hit that boundary at an angle that's greater than something called the critical angle. If you nail both of those conditions, get this, the surface stops being transparent and becomes a perfect mirror. 100% of the light gets bounced right back inside. No leakage, perfect reflection.
And this isn't just some weird physics oddity. It's literally the engine behind our modern world. You know the sparkle of a perfectly cut diamond? That's total internal reflection. Light gets in, but it gets trapped, bouncing around inside until it comes out the top.
The fiber optic cables that give you high-speed internet, they are just long, thin tubes of glass that trap pulses of light using TIR, guiding them for thousands of miles. And because that reflection is perfect, the signal is super strong. It's even used in high-end binoculars instead of mirrors, because no mirror is as good as the perfect reflection you get from TIR. Okay, on to another one of light's amazing tricks. This one also comes from refraction, but with a twist. You've all seen this. You shine plain old white light into a prism, and out comes a beautiful rainbow. This is called dispersion, and it happens because white light isn't what it seems. It's actually hiding a secret. That secret is that white light is actually a jumble of all the colors of the rainbow, all mixed together. And it turns out the light-slowing score of glass, it's a little bit different for each color. Violet light, which has a shorter wavelength, gets slowed down and bent the most. Red light, with its longer wavelength, gets bent the least. So the prism isn't creating the colors, it's just a sorting machine. It takes the jumbled up white light and neatly separates each color by bending it just a little bit differently, fanning them out into the spectrum we see.
So, let's recap. We've seen how light bounces, how it bends, and how it can be split apart into a rainbow of colors. For our final section, we're going to see what happens when we humans take those simple rules and master them, building incredible instruments that have totally changed how we see the universe.
The real game changer was figuring out that we could combine lenses. Instead of just one piece of glass bending light, what if we used 2 or 3? By carefully placing lenses one after another, we learned how to manipulate light with incredible precision. We could make tiny things look huge or make incredibly distant things look like they were right next door.
And of course, the microscope is a perfect example of this. It uses a combination of convex lenses to take something impossibly small, something right up close, and create a massively magnified virtual image that our eye can see. It's how we unlock the entire hidden world of bacteria, cells, and all the tiny things that make up our world.
Then you've got the telescope, which does the exact opposite thing. It's designed to see things that are unbelievably far away. And a basic telescope is just such an elegant piece of engineering. It's really just a beautiful application of ray optics, and it all comes down to 2 lenses, a big one at the front and a little one at the back.
So that big lens at the front, the objective lens, its job is basically to be a giant light bucket. Think about a star that's millions of light years away. The light from it is incredibly faint. The objective's job is to gather as many of those faint light rays as it possibly can and focus them all down to a single bright point. This creates what's called a real image inside the telescope, a tiny, bright projection of that distant star.
Then there's the eyepiece. That's the part you actually look into. Its job is much simpler. It just acts like a magnifying glass. It takes that tiny, bright image created by the objective lens and blows it up so your eye can see it clearly. And that's the whole magic trick right there. Step 1, gather the light. Step 2, magnify it. And boom, the secrets of the cosmos are suddenly visible.
And it's just incredible when you think about it. It all started with one simple idea. A ray of light travels in a straight line. From that, and just 2 rules for bouncing and bending, we've managed to build these incredible instruments that let our eyes see across the entire universe, and at the same time, down to its smallest building blocks.
So, this whole journey, just following a single ray of light, shows us how a few really simple rules can explain so much, from the color of a rainbow to the image of a distant galaxy. We've learned to bend and bounce light to our will. The only question left is, what secrets will it reveal to us next?